Hello everyone, this is the last lecture of the diodes, and we're going to do a couple of quick examples in this lecture. Okay, so this example is we're going to build a circuit called as a clamped capacitor circuit or DC restorer circuit. Okay, so the circuit looks like something like this. So you have input voltage connected to a capacitor, connected to a diode, and over here this is the output voltage, this is the capacitor voltage, and this is the input voltage. Let me define the input voltage and then we are going to see how our output voltage looks like and why do we need it. Okay, so the input voltage, let's assume, is this. Okay, so let's assume it to be minus 6 volt, 0, and plus 4 volts. Okay, and this region over here is 10 volts. Okay, so what is our clamped capacitor or DC restorer circuit will do? This circuit is going to, and we will see how this circuit will charge capacitor to its maximum negative value of the input waveform and clamp it to 0 volt, and that is why it's called as clamped capacitor. It's called as clamped capacitor. Okay, so what this circuit will do, and we will see how it is going to shift this waveform to the it is going to clamp or shift this waveform. First it is going to charge the capacitor to the maximum negative peak value, and whether it is going to charge it to the peak value, negative peak value, or the positive peak value depends on the direction of the diode it is connected. So in this configuration of the diode, it is going to charge it to the negative peak value, and then it is going to clamp it to shift it to 0 volts. Okay, so for example, this is how the output will look like, and I'm gonna shortly talk about, so this is what I'm saying. This is the output, how the output will look like. It is going to clamp it to the 0 volts. So what it does is it kind of shifted this entire waveform, this circuit, to the 0, and this is the new waveform that we got. Okay, notice that the average value of both of these waveforms are different. Okay, so how it does that? All right, so you can see that. So what will happen at when the input signal will start at when the input signal will start at minus 6 volts, the diode will turn on. When the input signal will start at minus 6, right? So this means that my diode will turn on, and the and it is going to charge the capacitor to 6 volts. So when input will start at minus 6 volts, this is going to make sure that the diode will be forward biased. Diode will turn on and charge the capacitor to 6 volt. Okay, so during this region, it is going to charge the capacitor to 6 volts. All right, now as it will move from minus 6, as it moves from minus 6 volts to 4 volts, right? During this entire time, as it is moving from minus 6 to 4 volts, what is going to happen is diode will become reverse biased. Look at the direction of the diode, right? So the potential over here will become more than the potential over here. So the diode will become reverse biased. Diode will be reverse biased and off. So this means that at that point in time, at plus 4 volts, the output voltage V naught will become equals to Vi plus Vc, which is plus 4 plus 6 plus 10 volts. Right, okay, so we got this and this. Now, during this entire time, the output voltage will remain constant. Now, when input signal again jumps back to minus 6 volt, diode will turn on again, right? And our potential drop across the diode now will be 0 volts. And it is going to go directly, it is going to jump to 0. The output is going to jump directly to 0. So this is output. So when input signal again jumps back to minus 6 volts, diode will be on and output will jump to 0 volts. Okay. Right, so what we have seen in this circuit is we can build a small circuit with a diode and a capacitor again, in which we are taking output across the diode and looking at this configuration of the diode, in which the anode of the diode is connected to the ground and the cathode to the capacitor. It will first charge the capacitor to the negative peak of the input waveform and then clamp it to 0. Now this clamping would have been in the opposite direction, right? For example, rather than going this, it would have gone in this direction if the diode would have been connected the other way. All right, so in this case, we saw that first during this time, during the start of the waveform, during this time, the capacitor was charged to 6 volts. Then it becomes, so that is why it got charged to 6 volts, and the diode was on, and that helped complete the circuit and the diode to charge and the capacitor to charge, sorry. Now during this time when it moved from, and during this time the diode was again on and a short circuit, so the potential drop across it was 0. When it was moving from minus 6 to 4 volts, it became open circuit, and the total potential drop across was a summation of the Vi and the Vc, and the total comes out to be 10 volts. So it jumped to 10 volts again. And now when it fall back again to minus 6 volts, the input waveform, again the diode becomes forward biased and it becomes on. So the potential drop across the diode again suddenly jumps to 0 volts. Okay, so this is called as a clamp capacitor or a DC restorer. And it has some useful applications. One of them is what the name suggests, for the DC restoration. For example, application DC restoration. For example, if we have a pulse signal that is being transmitted through a capacitively coupled, or we have an AC coupled system, for example, that system is going to lose the DC component it originally had. So what we can do is we can use such a clamping circuit to provide a specific DC component. We can design a clamping circuit to provide a specific DC component. So that is why it is called as a DC restoration and a DC restorer. It also can be used in pulse width modulation applications. So anyways, for DC restoration, just let me write down this a couple of sentences and then we can move to the next application. Right, so if a pulse signal being transmitted through capacitively or AC coupled system, it will lose its DC component. We can use a DC restorer circuit to add a specific DC component, right? So for example, this could be one of the applications, and second could be in pulse width modulation applications. So we are not going to discuss more on, for example, with specific pulse, how we can specifically use it for pulse width modulation, but something to remember. So anyways, the most important example is, for example, I can potentially give you a DC restorer circuit and give you a waveform and ask you what the output waveform is going to look like. Okay, so one last example and then we're going to finish it, which is something called as a voltage doubler. So we're going to design a circuit that is going to double the input voltage. Okay, so our circuit looks something like this. We have a capacitor here. We have a diode. This looks like a clamp DC restorer circuit that we have just seen, except that now look at the direction of the diode. It's connected the other way. And then we have another circuit. Now if I will look at the second part of the circuit with the diode and a capacitor, this more looks like a peak rectifier circuit. Okay, so this is my input waveform. We have a capacitor C1 plus minus Vp plus minus Vd1 D2, let's call this D1, C2, and V0. Okay, so we will see how this is going to double the voltage. Okay, so let me first start with the input waveform. So let's say the input waveform is something like this, so this is the input waveform and this is the peak value and this is the minus peak value. All right, so the first thing is that we can see that circuit has two components. The first component is our clamped circuit, and it has C1 and D1, right? And second component is our peak rectifier, which is composed of C2 and D2. Okay. All right. So now we have seen that in detail, that if I'm just going to consider this first clamp circuit over here, this portion of the circuit, and just consider what my VD1 will look like, considering this diode to be in the other direction, I can easily draw my waveform for this. Now what it will do is, it is going to charge the capacitor rather than to the negative peak. It is going to charge the capacitor to the positive peak and then clamp it to the negative direction. So it is going to clamp it to the negative direction. So this means that my output is going to look like, the VD1 output is going to look like something like this. Right, where no, sorry, this is slightly, I should have, okay, right, okay, so it is going to clamp the 0 to the peak value, right? So our next, essentially what our next 0 is going to be, it is going to be at minus Vp. Okay, so our VD1 waveform, this VD1 is going to look something like this. All right, where this thing is minus 2 Vp. Right, so what our clamp circuit did is, the positive peak is clamped to 0 volts, right? If we go back on this circuit, we saw that the negative peak, minus 6 volt, it charged the capacitor to the negative peak. If in this direction, when the diode was connected like this, it charged the capacitor to the negative peak and then clamped to 0, right? When now the diode is connected this way, it is going to charge the capacitor to the positive peak and clamp this positive to the 0. Now this essentially shifted this to the 0. When this positive peak shifted to the 0, then my 0 shifted to the minus VP and my minus VP shifted to minus 2 VP. So so the voltage that is going to appear across the diode D1 will look something like this. So this waveform is VD1, right? And negative peak will reach to minus 2 VP. All right. So our next is our peak rectifier circuit. Now we will know that if again I look at the direction of this diode circuit, we can see that what it will do is it is going to rectify, rather than rectifying this positive peak, it is going to rectify the negative peak, and the output of this V naught will be now 2 VP. It is going to charge the capacitor to minus 2 VP, and then it will remain constant. Since and it will remain constant because there is nothing else here to discharge the capacitor. And this is V naught. So the V naught will become minus 2 VP, and that is why it is called as a voltage doubler. Right, so our peak rectifier peak rectifier will provide, so peak rectifier output is across C2, and it will provide the total voltage and will provide the total voltage of minus 2 VP, right? And since it is double, then input peak, so it's called as voltage doubler. Alright, so we can use such kind of circuits, the voltage doubler kind of circuits, when we need higher amplitudes of our input signal. Okay, so this was the last example of the diode, and this finishes up our diodes chapter. After that, we are going to move to transistors. All right, so with that, thank you so much. I'm going to talk with you in the next kind of a section of our course, which is more focused on transistors. We are going to talk about two types of transistors, MOSFETs and BJTs. All right, so with that, thank you so much, and have a good rest of the day. Bye-bye.